Hi there, my name is Christopher Worst and welcome to the second video of Homework 2 of Transport 1. This video is going over Part 2, which is quite a simple little question, but kind of belies its complexities. Part 2 simply asks us to derive an expression relating the height of a ball in a rotameter to the volumetric flow rate. Now that sounds quite simple, but it's a little bit more difficult than one might think, and we're going to use a lot of the same expressions that we use in Part 1. So, per usual, I have behind me my whiteboard, or a whiteboard, and I'm going to start by drawing a picture and then laying out some of the framework equations that we're going to be using to fill in each other to then find that height of a ball to the volumetric flow rate. Okay, so I'm going to start by drawing a picture. Now, a rotameter is something that measures flow with by using a ball in it. So they usually have a very, very slight slope, much slighter than this, for their size, so that at the very bottom, somewhere in the middle here, the ball that is in the rotameter, that's a very big one, can rest on it. So it is, of course, cylindrical, and that is an absolutely horrible drawing, but it'll work for now. And then this ball, of course, has a cross-sectional diameter. We'll call it the diameter of the ball. And how rotameters work is that at position 1, we'll call this 1 with area 1 and pressure 1, and then also velocity 1, velocity of the fluid 1. The liquid comes in and then splits and tries to and passes through while pushing up on this ball to give space to pass through the little space here at space 2, which of course has its own area, pressure, and velocity of the liquid. It then passes through and continues traveling through state 3, which is, again, has its own area, pressure, and velocity, but it is unimportant for this specific situation, because what we're looking at is state 1 and state 2, because that is the biggest difference. So, we're going to be using Bernoulli's equation again, and we're also going to be using our old friend, the volumetric flow rate. So we know that volumetric flow rate is Q, and that is equal to V2 A2. And for this one, A2 is going to be a little bit more difficult, but we'll come back to that after I finish setting up the rest of the equations. We know that the Bernoulli's equation, as set up in Part 1, is equal to the pressure at state 2 minus the pressure at state 1 divided by the density of the liquid. I want to make that abundantly clear because there are multiple densities in this specific problem, plus the velocity at state 2 squared minus the velocity at state 1 squared divided by 2, again, plus the density of the liquid multiplied by gravitational constant, plus the gravitational constant multiplied by the height difference between between states 2 and state 1 is equal to the frictional heating, which of course is 0, so you can erase that. Now, finally, another simple thing for Bernoulli's equation and fluid dynamics in general is that the relationship between pressure and velocity is that V2, or V1, the velocity in A state, state 1, multiplied by the area of state 1, is equal to the velocity at state 2 multiplied by the area at state 2. We can then substitute this in for V1 to say that V1 is equal to V2 A2 over A1. So I will go ahead and substitute this in. So V2 squared, of course, because this is velocity at state 1 squared, multiplied by the area at state 2 divided by the area at state 1 squared. Now, if you notice as you look at the drawing, this area at state 2 is very, very small in relationship to the area at state 1. As mentioned in part 1, when you square a very, very small number, as is the quotient of A2 over A1, you get 0. So that means that this is 0, and V2 is, again, multiplied by 0. So this entire little value is equivalent to 0. That also means that the velocity at state 1 is small relative to the velocity at state 2. So we have this Bernoulli's equation. We have this flow rate. Like last time, we're going to want to solve for the V2, the velocity at state 2. We've used this, that's all we need it for. And to figure everything out, let's start with the flow rate so we have a path forward to where we're going. So, again, I'll write it just below it. The volumetric flow rate is the velocity at any given state multiplied by the area through which the liquid is flowing. We're going to want to find V2, that's fine. But A2, the area here, is the interesting thing. And to figure that out, we're going to need to pull some inspirations from the drawing here, which is going to be tough because it's not a great drawing. But either way, we know that the area here, or well, the area here in this state 2 is very, again, very small. So we really can't find it if we didn't have this ball here. So we have a cross-sectional diameter and cross-sectional area of the ball here. So we'll start with plugging that in. So V2, the cross-sectional area is pi r squared, or pi d ball, diameter over 2 squared. So that's pi over 4 diameter of the ball squared. Yes. So this is a cross-sectional area. Then the cross-sectional area of this is actually equal to the this cross-sectional area of the ball plus something. I mentioned earlier that there was a slope here. So as long as that is a linear slope, and it is in this situation, as it's not specified that it isn't, and it is on Rotameter, so it's easier, plus slope times the height, plus mh all squared. Now, all we need to do is multiply this out to factor it, and we have V2 pi over 4 that'd be pi over 16, I think it would be actually. Pi over 16. No. Yes? Oops, no, I set this up wrong. We do want this, but this is actually the diameter of, as it should, of the rotameter as it changes with height. So, pi over 4 diameter of the ball just the diameter of the ball plus mh. There. This, I was wondering why this looked dumb. This was going to be an awful factor. So actually, sorry. This cross-sectional area is the cross-sectional area of the pi over 4 dh squared minus pi over 4 the diameter of the ball squared. So now, I'm going to make this pi over 4 to factor that out, velocity at state 2, and then we can factor those across. Actually, no, this is not squared. So we know that dh is equal to d ball plus mh squared minus d ball derivative, the diameter of the ball squared. Now we can factor this. I was getting confused on what I was factoring. Goes to pi over 4 in terms of velocity at state 2, diameter of the ball squared plus 2 times the diameter of the ball times mh times the slope times the height plus slope squared height squared minus diameter of the ball squared. If that gets cut off, it's fine because the diameter of the balls cancel, and it goes to pi over 2, or well, let's make this q equals pi over 2 velocity at state 2 times diameter of the ball times the slope times the height plus the slope squared times the height squared. Now, this slope is very, very small. And again, if you square a small number, it becomes 0. So, this slope squared value becomes 0, which means this entire value of m squared plus h squared becomes 0, which only leaves us with the volumetric flow rate equals pi over 2 times the velocity of the liquid at state 2 multiplied by the diameter of the ball multiplied by the slope times the height. So, I am going to substitute that in here. That is the end goal of what we want. So, Q is equal to pi over 2 velocity state 2 d diameter of the ball multiplied by slope times height. And with that, we have that copied, and I can erase all of this and get to work on the Bernoulli's equation and massaging it to get V2. So we have, and all of this here is pretty straightforward. So the first thing that we want to do is note that the difference in height between state 2 and state 1 is, again, very small. So we're going to ignore it. So this is 0, which also means that this entire value goes away. So we're left with the difference in pressure divided by the density of the liquid plus the velocity at state 2 squared divided by 2 is equal to 0. That means that when we take that, and I'm going to transcribe it down here just so I can move with it. That means that V2 squared over 2 is equal to the pressure at state 1 minus the pressure at state 2 divided by the density of the liquid. Oops, that's an awful row. And density of the liquid. And this, of course, to isolate V2 is equal to square root of 2, difference in pressures between state 1 and state 2 divided by the density of the liquid. And I'm going to erase this because I don't need it anymore. I'm going to move this up. So we've got V2 is equal to square root of 2 multiplied by the difference in pressures between state 1 and state 2 divided by the density, density of the liquid. Man, writing is not my strong suit today. I can erase this. So now we, again, there. So now we have this, we could substitute it into here, but we still have this pressure 1 and pressure 2 that, while it may seem that they're changing variables, and they are, there are more variables that go into them than would actually make this volumetric flow rate easier to find. So we're going to start with actually and move on to a force balance. So we have two forces acting here. We have the weight of the ball and the buoyant force pushing up against it. And we want a stable state. So they're going to cancel out. So buoyancy equals 0. So what we need to find is the weight of the ball and the buoyancy. Buoyancy force. Now we'll do buoyancy down here, the weight up this way. So the weight of the ball is pretty simple. It is just the difference in density between the liquid pushing, the liquid, and specifically the weight of the fluid displaced. So it's the density of the ball minus the density of the liquid multiplied by the volume of the ball times G. Much like rho GH is the pressure. This goes to, of course, density of the ball minus density of the liquid. The volume of the ball is the volume of a sphere, which is pi over 6, or pi over 3, it's the diameter of the ball squared times pi over 6. So pi over 6, diameter of the ball, well, cubed, times g. So we have this weight. And then the buoyancy force is a little bit more complicated. It is, going back to this picture, it is the pressure at state 1, the difference in pressures between state 1 and state 2, multiplied by the cross-sectional area of this ball. So that means that it is P1 minus P3, difference in pressures, multiplied by the cross-sectional area, which is pi over 4. Diameter of the ball squared. Now, this equation is useful, but P3 doesn't show up anywhere else in this, so it's not really useful for us. P2 does show up, and we do want it to cancel over here in this V2. So now we have to figure out a way to equate P1, P2, and P3. Well, oddly enough, because of this scenario, and because all of the liquid in this state 3 comes through state 2, the pressure at state 2 is equal to the pressure at state 3. That means that P1 minus P2 over multiplied by pi over 4 times the diameter of the ball squared is the buoyancy force. So now we have this, and we're going to equate them together over here. So the weight, the density of the ball minus the density of the liquid times pi over 6 times the diameter of the ball cubed times g is equal to difference in pressures P1 minus P2 between states 1 and 2 times pi over 4 times the diameter of the ball squared. Now, these two are going to cancel to leave a diameter of the ball to the singular power, pi's cancel, and this 4 to 3. So now what we want is we want P1 and P2 to cancel up here, or to be substitutable up here. So that means we can substitute this across to have P1 minus P2, or the pressure difference between states 1 and state 2, is equal to 4/6, or 2/3. 2/3 times the density difference between the ball and the fluid, or the liquid, multiplied by the diameter of the ball times g, and we're going to bring that up into here. I am simply going to write it right next to it. That means that v2, the velocity at state 2, is equal to square root of 2 multiplied by 2/3 diameter of the ball times g multiplied by the density of the ball minus the density of the liquid divided by the density of the liquid. Might be in the way here. This, of course, is just 4/3 here. So now we have this V2 and this Q, this volumetric flow rate, and just for completion's sake, we'll plug it all in just so we can get one nice long equation that summarizes everything. So, Q is equal to pi over 2 times diameter of the ball times the slope times the height times the square root of 4/3 diameter of the ball times gravitational constant times the density difference between the ball and the liquid divided by the density of the liquid. All told, that's what we were aiming for. And with that, part 2 is finished. Thank you very much for watching. I hope you have a wonderful day.